Swayam Prabha. Digital India. Educated India.
Okay, good morning, and we have seen so far several kinds of biopolymers derived from plants, animal origin, marine origin, and also we looked at various bio-based non-biodegradable polymers also. Okay, we looked at a lot of chemistry, a lot of separation, extraction processes. So, end of the day, what you want to do with these polymers is that you want to make a product out of that, right? You want to, let's say, cast a film, or you want to make a, let's say, a bottle or a container or a sheet or a tube, right? So basically we want to use these biopolymers in certain product form. So now that we can only do with the processing equipment. Okay, so we need a set of processing equipments that will take this polymer and convert them into a product. Okay, so now the existing machinery that is available for conventional plastic are usually used for bioplastics also. Okay, we don't have a separate machinery for bioplastics. We can use the existing machinery that are designed for conventional non-biodegradable polymers, but then use it for biopolymers also. Okay, so in that context, I want to take few lectures on various types of machinery, right, that takes the biopolymer pellets, granules, powder, convert them into a product. Okay, so the first one I want to talk about is extrusion. We have seen extruder in the industrial visit to Ascent Materials already, and but even without that, this extrusion is not very different from what we do at our kitchen, right? So you have seen this process. Okay, so if you have tasted idiyappam or sevai, this is how it's made. So it's basically a wooden or a steel cup. Okay, it's a hollow, and the bottom you will have a screen, okay, with certain holes or particular shape and size, and then there's a plunger that you put your dough, typically a rice flour, and then you basically press hard. Okay, then you basically see that you get the strands extruding out. Okay, so this is the way that many of the food products, spaghetti and the various other things are also made. Okay, so we are basically pretty much talking about this. Only difference is that this is typically done at a room temperature, and empirically we know how to do these things. But then the same operation, when we do it for polymers, there are certain other conditions we have to take into account. Okay, so keep this in mind, that extrusion is nothing but making of idiyappam, right? All right, so now let's go to the little technical details. What do we mean by extrusion? How is it defined? What are the instruments that are available for extruding polymers? So the word extrusion basically means that we take a material, typically a polymer, and we soften them or we melt them, either way. Okay, so that it is flowable, it is deformable. Okay, then what we do is we actually apply a pressure, we force them through an orifice, and this orifice is called also a die. Okay, in the previous example of this idiyappam machine, the screen that has its holes are the die. Okay, that kind of confers the shape for the extruded material. Okay, and usually it is under certain pressure. You're going to apply a pressure, you're going to melt it, and then you're going to force it through an orifice. So that whole process, we call it as an extrusion. Okay, so now if you ask how is this melting or softening happens, it is usually through a thermal process. Okay, we apply heat, and then the material becomes soft or it melts. This heating can be of two mechanisms. One is you can actually provide external heating elements, resistive heating or electrical heating, or sometimes the material can actually have a very viscous nature. By simply applying a pressure, there is a heat of dissipation, viscous dissipation, that can also increase the temperature of the material, thereby melt. Okay, so the heating typically involves this external heating or viscous heating. You can also think about other kinds of heating. For example, you can actually use steam to heat it, you can use microwave, you can use induction. Various other thermal mechanisms are also possible, but commonly electrical heating and the viscous heating are the dominant mechanisms. Now in this extruder there will be a screw, okay, and we will see the pictures shortly, and the role of this screw is to generate or apply pressure that can overcome the fluid friction. Okay, so now the molten polymer is very viscous, highly viscous. For it to flow, it will have a lot of fluid friction, and you have to apply enough pressure for it to flow through a orifice or through a die, and the screw actually does the job. Okay, now we call this term extrudate, which is nothing but the material that is basically being extruded. Okay, and this could be of very many kind. It can be a thermoplastic. We know what is thermoplastic. Thermoplastic is basically a polymer. When you heat it, it becomes soft and flowable, right? That's thermoplastic. And unvulcanized rubber. Unvulcanized rubber means uncross-linked rubber. Okay, you can also do lead, metal like aluminum, and foodstuffs like we said, right? The spaghetti and rice flour and other things also. Okay, so all these, whatever that material that we extrude them, we call that as an extrudate, right? And in invariably, whatever be the polymer, whether it's biodegradable or bio non-degradable, whatever that be, the final process of that polymerization will be formation of a pellet. Okay, so if you have seen the polymer, it's mostly sold as a pellet, okay, of a particular size, maybe in centimeter or a few centimeter. So the final product is usually made through an extruder, which is called pelletizing. Okay, for example, let's say you go to take some cornstarch. Okay, so you take corn and then you do some chemical processing, extraction, acid, all that. End of the day, you're going to get a powder. Okay, but you don't sell powders. You want to granulate them. You want to make them into a pellet. So what you need to do is you basically send this powder through an extruder and then make them into a granular form, which is what we call as a pelletizing. So extrusion is a very crucial step for the final processing of any polymerization reactor, right? And then we also can actually add sometimes additives to the polymer to make alloys, blends, fillers, and pigments. Pigments, we add them because we want to add a color to the polymer. Okay, basically a dye stuff. Fillers, we want to, let's say, increase the mechanical property, we want to reinforce them, so you add a filler. Sometimes you want to blend more than one polymer, okay, maybe 2 polymer, 3 polymer, you want to make a blend, physical blend of that. Okay, so all this process can actually happen through an extrusion, which is basically affects mixing of the multiple components. Now, extrusion profiles. So when you extrude, what are the forms in which you can extrude? Well, you can actually extrude films, you can extrude into fiber, you can see tubing and pipes, all this can be extruded. What we saw in ascent material was extrusion of a nylon fiber, okay, and that was cut into smaller pieces to make granules, right? Now this extrusion process, as we know in chemical engineering, we talk about continuous process, we talk about non-continuous process, or in other words, batch process and continuous process. Similarly, the extrusion can also be a continuous process where things can go on continuously, or it can be a batch process also. Okay, so the extrusion of fibers and then pelletizing it is a continuous process. You keep on feeding the material, the extrusion will create these strands, and the strands can be cut into smaller pieces. It just goes on and on as long as you keep feeding the raw material. Okay, there are other extrusions called blow molding or injection molding, which is basically a non-continuous process, or it's a batch process. In the case of a blow molding, let's say you want to blow mold a bottle, so you'll have a small preform, and that one preform is actually processed to make a bottle. Then you stop the thing and then load the new preform and do it over. So you do it in a batch wise. Similarly, in injection molding also, you have a die, okay, and then the die is filled with the molten polymer, and you allow it to cool, then remove the parts and again do it again. Okay, so that is done in a batch wise. So overall, we can say that the crucial element in the extrusion process is the extrusion screws. Okay, and that is very important mechanical element in the entire polymer processing. Okay, so these are some of the basic facts about what extrusions mean, right? So now going to some details, you will see that there are different types of extruders, and these extruders are the classification of extruders depends on what is whether it has screw or not screw based, or whether it is a basically what is the mechanism of operation. Based on that, you can have different classifications. For example, the first kind is called the screw extruders. That means this extruder will have a screw, and the role of the screw is to generate enough pressure so that you can pump or you can push the polymer through the orifice. So here you have two kinds. You have either a single screw in the entire extruder, or you can actually have more than one screw also. Okay, so you can have twin screw or multiple screw also. So this classification is based on how many number of screws are there in the extruder. Then there are other extruder in which there is no screw. It operates differently. Okay, for example, this disc or drum extruders are continuous methods, but here the mechanism is based on viscous drag or elastic melt extruder. There is no screw, but these are not very common compared to screw extruders. Okay, conventionally screwed extruders are the most common, and there are something called reciprocating extruders. Within that, these are basically these are mostly discontinuous or batch, because the example of a reciprocating extruder or non-continuous extruder is the one I showed in the beginning, right? That the idiyappam making machine, where you load the material, you extruded it, and then you stop it, refill it again, and then do it over. So that's a batch process. Okay, in fact, that kind of a extruder is called the ram extruder, because it basically there is a ram, there is a plunge that rams against the material to push it. And there are also reciprocating single screw extruders. So this is a broad classification of extruders, but the screw extruder by far dominates the market in terms of number and types. So now let's go to the single screw extruder. The single screw extruder, as you can see, it contains basically a screw element. Okay, it's called Archimedean screw. So you can see that it's basically a shaft. On the peripheral of the surface of the shaft, you have this helical blade or the helical winding, and it's basically, you can see there is a red ball. Let's say you have a small particle or a water droplet or a polymer particle, and you see how it gets conveyed. Okay, so this is basically a mechanism that actually conveys a solid from one end to the other end through a screw mechanism. So a typical single screw extruder will have mainly three important things. So you have something called a hopper, okay, which has the reservoir of the raw material, okay, the powder, the pellet, whatever that you want to extrude, that is basically filled here. That is one end of the extruder, and the other end is what we call as a die, where the molten polymer is forced through. Okay, and then you have the screw, which is the most important element. The screw is supposed to take the material from here and then conveys it from this end to the other end. Okay, so now when it happens, some thermal process happens from the beginning to the end. You can see that there is a barrel. So the one that I am highlighting here, that is a barrel which is stationary. Okay, so this is a barrel, and there's a screw is actually set inside. So if you take a cross section of this, you will see that there is going to be this is the screw, and then this is your barrel. Okay, and the polymer is supposed to go through this annular region. Okay, if you take a cross section, right? And then you also see that there are a lot of heating elements here which are kept as a modular. That means you can actually control the temperature in each zone separately. Okay, typically in extruder, the temperature increases from the one end to the other end. At the feed location, the temperature is low. As you go to the towards the end of the die, the temperature actually increases. So therefore, you can control the melting and the physical state of the polymer. And then on this side, you have a variable speed a motor that allows you to control the speed of the rotating screw. Okay, the screw is rotated at a particular speed, and this is through a drive motor. It could be AC motor, DC motor. There is a gearbox mechanism that actually allows you to change the speed as well. And then once you have this, so you have this raw material coming in, and the screw will push it, and then the barrel has a different temperature. This temperature can be applied through electrical heating, or it can be through a viscous heating. Okay, and then it basically goes through this die, and then once you get this extruded out, typically you take this material and then send it to subsequent auxiliary operation. For example, it can be sent through a cooling water so that the extrude can be cooled off and solidified, or you can actually have a kind of a pulling mechanism so that you draw and then do just a winding of this into a fiber or a sheet, okay. Or you can also send it to a cutting machine, so you can make a small pieces of the pellets also, okay. Or if you want to continuously wind them, that is also possible. So typically you have certain other additional accessories to take this extruded material and then convert them into a product. And die is something important. I'll come back to this little later, what it can do. Now, so here we are looking at a little bit deeply about the single screw extruder, and what I have shown in this figure, the screw is actually somewhere inside. So now the screw is actually shown separately. You can see that the screw is not of a uniform width, okay. You can see that up to this point it has a same diameter, and then from here to here you see the diameter slowly increases. You can see this diameter increases from here to here, and then in this in the further subsequent section again it becomes constant. So you have a constant dia, increasing dia, and then constant dia, okay. But all along the barrel diameter, that remains the same, okay. So what that means is, somewhere here you have the barrel here, and then this is your screw cross section. Somewhere here this gap, the annular gap, becomes smaller, okay. So you see that now. So here the polymer actually goes through this annular space, which is more wider. As it comes to this middle section, this gap becomes now smaller, okay. So again here and it actually keeps changing from small to, so from big to small, and then subsequently in this final section it is a constant width, okay. So what is the reason to have such a design is because what we want to achieve with this screw principle, okay. You can see the main functions of the screw is that it first receives the polymer from the hopper as a pellet or a granule, or it can be a powder depending upon what you want to extrude. And the main function of screw is to thoroughly mix the solids, okay. You can have a single component, you can have multiple component. As the material is carried through, it should have sufficient homogeneity or mixing thing. And also this must completely melt the material, and then also to increase the pressure so that it can overcome the friction resistance at the die. So I already told you that one end of the extruder has a die, okay, and the die will have a certain perforation, certain profile. When you push the fluid through that, you're going to have a lot of resistance, okay. So that means you have to create enough pressure for the polymer melt to go through, okay. So the screw actually does that job, and then pump the mixed melt through the die at certain temperature and pressure that you decide, okay. So now in order to do this function, the screw section can be divided into three parts. There is something called feed section or feed zone, that is the first one. Then we have something called a transition zone or a compression zone. Then we have something called pumping zone or the metering zone. So most of the single screw or double screw extruder will have all these three parts: the feed part, the transition part, and then the metering part, okay. So what's happening along this is that the gap between the screw and the barrel, that changes. Also the temperature also changes, okay. And we do this change of temperature and changing of the flow path so as to control the pressure, to control the thermal state of the material, right. So here if you look at more deeply, you see that in the feed zone, the resin or granules or pellets, these are compressed to force the trapped air to a hopper. So what it means is, in the beginning, in the very beginning of the extruder, the role of the screw is to compress the solids just enough that any trapped gases or air can actually come back, so that you don't have any bubble formation in the final product, okay. And then sometimes the raw material that you have in the hopper may be aggregated. It may have an agglomerated state, and you want to break that into a smaller pieces so that you can have effective mixing as well as melting. And homogeneous mixing of individual components is also completed in the feed zone. The feed zone is here, okay, where the diameter of the the screw is actually constant, and the gap between the annular space between the barrel and the screw is also constant, okay. So then comes this transition zone or compression zone. So here what happens is, the channel depth tapered gradually. Okay, so that means you can see from here to here there is a small increase in the diameter of the screw, and this will actually lead to something called a compression. Okay, and this compression is quantified by a factor called compression ratio. This is nothing but the flight depth at the feed location divided by the feed depth in the metering section. Okay, so this basically tells you to what extent you are actually restricting the space to flow in the metering section versus the feed section. Okay, so this compression ratio can go anywhere between 2:1 to 6:1. So 2:1 means the gap here, you see this gap between the barrel and the surface of this is the depth in the feeds location, and this is the location at the transition, and here is the location at the metering section. Okay, so from the feed to the metering depth, that ratio we call it as a compression ratio. Okay, so the compression ratio can be 2:1 to 6:1. And because we do this change of the dimensions, we will have an intense heating and friction. Okay, because you are forcing the material, the speed of the screw is the same. Whatever material that is flowing through the feed will have to go through the other sections, but then at a smaller gap. That means you are actually pushing it against a smaller gap, so that will increase fluid friction, that will lead to viscous dissipation, that will lead to increase in temperature, and that will lead to melting also. So typically in the middle section, the melting is completed and T is raised to the die temperature. Okay, so in this particular zone, the temperature is gradually increasing, the pressure is also gradually increasing. Okay, but then you also want a section where the temperature and pressure becomes a little stable, so that when the material goes through the die, it has a constant temperature and constant pressure, and that's what happens in the metering zone. Okay, the purpose of having the metering zone is to stabilize the temperature and pressure that is needed, and that's why here the depth is constant. Here the diameter of the screw and the barrel is constant. Okay, so melt is homogenized and temperature and pressure is stabilized, so now it is ready to get extruded, right? So these are some of the dimensions. When we think about this, when we ask, when we try to buy extruder, we typically mention what is the dimension of it. The dimension is related to the diameter of the barrel and the length of the barrel. Okay, so typically the diameter of the barrel, so remember the barrel is nothing but this, the one that I have shown here in blue color, right? That is a hollow cylinder in which the screw is rotating. Okay, and typically the barrel diameter is constant, but within that the screw diameter can keep changing. Okay, so now an extruder can be designated or represented by the diameter of the barrel. Typically this diameter can be as small as 0.75 inch, or it can be as big as a 24-inch barrel diameter. Okay, and in the extruder that are typically manufactured in the Europe, they go anything between 2 to 60 centimeter from the low to the highest. But in the industrial scale, typical diameter of the barrel can go anywhere from 1 to 6 inches, or in other words 2.5 to 15 centimeter. And then the length of the extruder is expressed in terms of L by D ratio. L by D is nothing but the length of the barrel divided by the diameter of the barrel. Okay, it's like an aspect ratio. Okay, and this ratio can be anywhere between 20 to 30, and 24 is a kind of standard size. Okay, so when we say 20, it means the length of the barrel is 20 times more than the diameter of the barrel. Okay, that's the aspect ratio. So when you see a paper on extrusion of a polymer material, the extruders are basically characterized. We use the extruder of a diameter of particular, let's say 1 inch, and with an L by D ratio of 20, and then they will also say that in the barrel the temperature distributions are in the feed zone 120 degrees Celsius, in the compression transition zone the temperature was this, and in the metering zone the temperature is something. So we specify at least 3. It can be actually even more than 3 also. Okay, so you can if you remember when we talked about PLA resins, the PLA manufacturers will tell you, if you want to extrude this polymer, these are the temperature setting you should have in your extruder. Okay, that relates to the thermal properties of the material. You do TG analysis, you do DSC analysis, you understand what is the thermal properties of the material, where is the melting point, where is the TG, where is the decomposition temperature. Based on that, you have to operate your extruder. So now we can go a little advanced design of this extruder. What we saw is a very primitive design, but typically what happens is that when you extrude, you are increasing temperature, and the polymer that you have may not be of completely single component polymer. It may have certain other additives that may volatilize, that may become volatile, and they may want to evaporate. Okay, and if you don't remove that vapor, that bubble can get integrated into the product that you make. So you need to have some provision in which you can actually let that vapor go out, the volatiles to go out. So that leads to the formation of these vent ports. Okay, so in this particular extruder, there's only one vent port, but you can actually have many of them. The idea is to see that there you have a feed hopper here. Okay, so this is actually driven by a motor, and then you can see that this is the feed zone, then you have a transition zone and then metering zone. You can also see that in somewhere here the diameter of the screw has changed, and then there is some gap here. So any volatile that has created during the heating process of this section can now easily escape. Okay. So sometimes what happens is that when you produce polymer, when you do polymerization of a monomer, all the monomer may not be polymerized. You may have still some unreacted monomers and oligomers, which could be highly volatile, okay, at high temperature. So you can remove these monomers and oligomers, reaction byproducts, even moisture sometimes, and then some other residual solvents. All these are all volatiles. Okay, so you should have some sort of a vent-like mechanism to remove this. Sometimes we can also use this vent ports to actually add extra additives. This polymer may not have any volatile compound, but if you have an extruder with a vent port, that vent port can be used to actually mix fillers and additives and other reactive compounds. Okay, for example, you don't want to add, let's say, one option is to add the filler and other things in the feed hopper itself, but sometimes if you want to add something when the polymer is nearly in a melt condition, you can actually use this vent ports to introduce the filler and other blends and other additives. Now, one problem with this vented single screw extruder is that sometimes when the screw is operating, it's increasing the pressure. Sometimes the molten polymer can also come out of this. Okay, if the orifice is big enough, you can also escape through that. So that is something that you have to be cautious, and that's why you see here the diameter of the screw is now decreased, so that the pressure can be reduced locally, so that only the volatile goes out and the polymer does not go out. Okay, so that's something we have to keep in mind. And because of this provision of vent, the L/D ratio can be little higher than the non-vented extruder. The extruder with no vent port, we said L/D ratio can be between 20 to 30. When you have vent ports, you have between 40 to 50. Okay, and sometimes this vented single screw is more versatile. You can actually buy that. You can even close those ports. If you don't need them, you can just close those ports. You can still use it as a regular single screw extruder. Okay, and then if you want to say you want to work with a new kind of polymer which may have a volatile, at that time you don't have to change your extruder. You can just open that vent wall and then use it. So it is more versatile than the single screw extruder. Now the two previous example we saw is typically for thermoplastics. Okay, but let's say you want to extrude rubbers. Rubbers are nothing but elastomers. Okay, and typically rubbers have much higher viscosity than thermoplastics, even 1 or 2 orders of magnitude higher. Okay, so the moment the viscosity goes up, the viscous dissipation or heating due to viscous dissipation will also go very high. So because of that, the heat generated will also be very high. Because of the reason, the extruder that are designed for rubbers are usually shorter than the thermoplastic extruders. Okay, for example, the L/D ratio can be anywhere between 5 or maybe 15 to 20. It also depends on whether the rubber that you fill in is under hot condition or cold condition. Okay, if the feed itself is hot, L/D ratio 5 is good enough to extrude the rubber. If you have a cold feed rubber, the L/D ratio can be between 15 to 20. and typically the extruder temperatures are a little lower compared to thermoplastics. Thermoplastics such as like the polyethylene or polypropylene, you will do up to 200 or 220 degrees Celsius, okay, around 200, but rubbers are typically done at 100 and 120, okay. And so here you will see that this is a kind of an example of an extruder for rubber. If you see here, unlike the single screw extruder for thermoplastic where the barrel diameter was constant, and you see that the diameter of the screw changes from one end to the other, okay. But for extruding rubber, what happens is you don't change the diameter of the screw, the diameter of the screw remains the same, but you see the pitch, which is basically the distance between two subsequent turn, that keeps diminishing as you go down, okay. So this is called constant depth. Depth basically means the distance between the barrel to the surface of the screw, okay. So let's say if the barrel is somewhere here, this is the depth which is constant along this length. But if you look at the pitch, which is the distance between the subsequent thread, that changes, okay. So that is a typical design for a extruder of a rubber. Sometimes there are extruder in which there is a barrel fins, okay. So you see that this is the barrel in the top and bottom, and you see that there is some provision set here to restrict the flow conditions, okay. There are kind of fin like structures that are on the inner wall of the barrel, and then you have a screw rotating at certain speed, okay. So this is called twin barrel extruder, especially for rubbers. This is basically shows the cross section of the same thing. So these are all the fins that are protruding from the inner wall of the barrel, okay. So instead of the barrel being hollow, you basically have baffles and pins coming from radially inward, okay. So but you can see that it is placed in such a way that the screw does not break them. And there are something called cross channel barrier, in which case some of the screws are actually cut in between so that the material can actually flow a little complicatedly, in a complicated way. So you can see that here the screw is cut here, so the plastic can actually flow this way as well as this way. Similarly here there is a small cut, here, and the polymer can go between the screw laterally also, okay. This is just to kind of change the flow pattern of rubber like materials. So now this is another important thing is to see how the die which actually forms a product of desired shape and size is coupled with the main extruder body. So far whatever we have seen is something called inline extruder, where let's say this is your hopper. Maybe you can look at this as like a top view. From the top view, from the hopper, the material basically comes down all the way here and then reaches the die, and then the product comes out, okay. Everything is in line. That's why it's called inline extruder. Now you can also have a situation where the hopper is here, the molten polymer comes here, but then the die is actually facing this way, right. So this that means that the die is actually pointing this way and the extruder is pointing this way, okay. Or you can also have a little angle. So you can see that this extruder is at an angle theta, is also at a particular theta, okay. So why we need that is because suppose you want to coat a wire with a polymer, let's say electrical wires, okay. You have a metal wire and then you want to sheath or you want to put a coating of a polymer, then this arrow can represent a flow of a metal wire, okay. And this kind of a rectangle or this kind of a right angle or angled extruder can actually form a coating or a layer on the surface of this metal layer, okay. And then gives a continuous protection of core shell kind of structure, core being the metal wire and the shell being the polymer layer. You can also do something called co-extrusion. If you have more than two polymers and you can have two extruder, and the two of the extruder can actually come together, it can form co-polymer. You can have a product that is formed through co-extrusion, or you can also have three of them, 1, 2, 3, okay. So these are different arrangement with which you can align multiple extruder to create this. Okay, next. So far what we have seen is a single screw extruder, but then there are also multiple screw extruders. One typical example is called this twin screw extruder. So twin means two screws. Okay, so you can see that there are two screws across this extruder, and this extruder can the two of them can actually rotate in the same direction, which we call co-rotating extruder, or it can be that one screw rotates clockwise, the other screw actually rotates counterclockwise. Okay, and typically we have such a configuration because we want to blend additives effectively, homogeneously, or maybe fillers or reinforcements, or sometimes blending of two or more polymers. Okay, so twin screws are very famous, very common in creating formulated polymers with additives, and they also will have the same kind of hopper. It goes through melting of the two, mixing of them, increasing the pressure, send it to the dye, and then it granulates. Okay, so that is one example. And you can also have a little bit more complicated designs of multi-screw extruder. One such is called a planetary roller extruder. So here you have the feeding location somewhere here. Okay, so this is a hopper. So in the hopper, so the material actually flows in this direction. Okay, so here in this first section, this is like a very similar to a single screw extruder type. Okay. Now once you have a particular point, then this enters into another set of screw. So what is happening here is you will have the main screw. On the main screw, along the peripheral, you can actually have multiple screws also. Okay, for example, if you take a cross section of this, you will have a main screw that is coming from the previous section, and then you can have few other screws also rotating. So here I have just drawn some 5 screws. Okay, this is a normal, it's going normal to the screen. Okay, so from the side view you are seeing only the 2 screws here. Okay, so that's why it's called, the main screw is called the sun screw, and all these additional ones, these are called planetary screws because they are actually on the periphery of the main screw. Okay, so the main screw is rotating. On the surface, each of the smaller screws are also rotating. Okay, and the reason to do that is now the material will flow through the gaps between the main screw and the planetary screw, and also between the planetary screws. That creates a very complicated mixing pattern, so that the material, when it comes out of this discharge unit, then you have a very good mixing. Okay, so this is one such example of a multi-screw design. There are many other designs also, but depending upon the the kind of material that you want to process or extrude or mix, you can also have either this twin screw or this kind of multi-screw extruders. So now we are looking at now second kind of extruder where there is no screw. Okay, without a screw, can you extrude a material? Can you mix material? Yes. One example is something called this disc extruder. Okay, so disc extruder basically has 2 discs. One disc is flat, okay, and that rotates. The other one is stationary, but this other disc is not planar. It actually has a stepwise cuts. So you can see here, you can see it's like a pizza, and then you have removed few pizzas. Okay, so you see there is a gap, and there's a step, gap, step, gap, step. Okay, so imagine you have a plate, and then you have cut a conical section, a triangular section from here. Now your mix, so you can put your you can put this assembly, the flat one along with the stepped one, and one of the top one rotates. When it rotates, you can see that this is a section where you have this kind of cut portion, and this one actually corresponds to this particular area. Okay, so when you think about the top, this is the top one, the flat one that's rotating, and this is the bottom one which has this cut. Okay, so when the polymer is actually introduced here, it has to go through here to here, and you can see that the velocity profile changes because the same mass is entering from high area to low area, the pressure will increase. Okay, and then if you have this kind of exit channel, then the polymer can actually flow through the annular space, and then it can extrude into from the middle point of it. Okay, so here there is no screw. It is a very simple action of 2 discs, one of them rotating, and this rotation is not happening between 2 plates, but only one is flat the other one is stepped, and the gap difference will actually increase the pressure, and then the extruded material will come through these things. So you can see that there is a channel provided here in each of these sections, and the polymer will flow through, reach the center, and then come out. Okay, so this and this are the same thing. This disc is shown without the disc, without the steps. Okay, so this is shown to highlight the exit channels. So this is one example, and you can see that how the pressure increases when the distance goes from here to here. Okay, so but this extruder is not very common. It is there in certain special applications. Other example is something called drum extruder. In the drum extruder, you have this hopper here. You have hopper here. Okay, and then you have a shaft. Okay, so this is a cross section view. Okay, a shaft is rotating such a way that there is a gap between the body outside and then the shear. So the material is taken in because of the shaft is rotating. The material is taken in and comes out here. Now here you have a knife, okay, to scrap this polymer, and because of that the polymer will actually flow out here. You can put a die here and then extrude into certain shape. So here also there is no kind of a screw like a mechanism. It's only a shaft that rotates, so that, or shaft or a drum if you call, and then the polymer gets squeezed in through this rotary action, and here we have a kind of a restriction so that the polymer does not come out here but then goes to the other side. Other possible designs are such that you also can change this width here. So in this design, the width between the drum and the barrel are the same, but here you see it kind of diminishes as this goes up. Okay, so that means the pressure can gradually increase from here to here, and then it can be extruded. Okay, so these are some examples of drum designs. Now finally, the ram extruder. So we talked about three kinds of extruders. The one which is based on screws, the other one is based on disc or drum. The third one is this ram extruder. As I said, ram extruder is nothing like you have a barrel, you fill your billet. So billet is nothing but the material that you want to extrude, and then you put a plunger, you put a piston like arrangement, and you apply pressure. Okay, this pressure can be a mechanical pressure or a hydraulic pressure, and then you force it through a die that you want to do. Okay, it's a batch process because you do once, remove it, fill your material again, and do it over. Okay, so this is an example of single arm extruder. You can also do multiple arm extruder also. So you can see that there is one arm here, there is another arm here, and then you can actually push in two different directions, and then you can have the mixture coming out of this die. Okay, so again, compared to the screw extruders, these ram extruders and the disc extruders are not that common, but you should probably know that there are other kinds of extruder also. Depending upon the function, thermal stability, you may want to look at other designs also. That's the context. So that's all I had to say, but these are all very theoretical, but like in chemical engineering we do performance calculations of any equipment. Here also for extruder also there are performance equations. What goes in is momentum balance, heat balance, and rheology, all that goes in to predict the temperature profile, flow rates, and viscous dissipation. All that can be included. Typically such calculations are a little complicated. We cannot do it in pen and paper. It has to be done through numerical or based on a software. Okay, and I think this course, since this course is not about designing of extruder, I am not going to discuss those topics, but if you are interested, you can see there are books written on extrusion processing, and you see a detailed modeling of the entire process. You can calculate the mass flow rate, the temperature buildup, the pressure buildup, okay, and you can do some finite element method simulations also to see how the temperature builds up to, if you are into design of an extruder. Okay, so with that, I'll stop here. Thanks.